Simplified, where we walk through Leetcode problems the easy way. Today, we're tackling Leetcode 35, Search Insert Position. It's a classic binary search problem, and once you understand it, you see how elegant and efficient it really is. The task is simple. Given a sorted array of distinct integer and a target value, return the index of the target if it's in the list. If it is not in the list, return the index where it would be if inserted in order. Let's use binary search because it's perfect for already sorted lists. Start with the left pointer at index 0 and the right pointer at the very last index. Now we enter a loop that keeps going as long as left smaller or equal to right. Inside the loop, find the middle index. If the middle element equals the target, great. We just find the target. Return the middle index immediately. If the target is smaller than the middle element, move the right pointer to the left of the middle because we need to search the left side of the middle. If the target is larger than the middle element, move the left pointer to the right because we need to search the right side of the middle. If the target is not in the list, the while loop will finally come to an end. The left pointer now will be where the target would be if inserted. Now we step through this algorithm using the below example. Watch carefully. This is where the logic becomes crystal clear. Define the left pointer, point to the very first element, and the right pointer, point to the last element of the list. As long as the left is not greater than right, do the following. Calculate the middle index right here. Compare it with target 5. 5 is greater than 3. Then move the left pointer to the right side of the middle pointer. Left is still smaller than right. Then recalculate the middle pointer. At this time, it will point to 5. And now compare 5 with target 5. We found it, we return the index of 5 within the middle. 0, 1, 2. We return 2. Moving on to the next example, we need to find 2 inside the array. First, set up the left and right pointer, which point to the first and last elements. Now enter a loop as long as left is smaller or equal to right. Find the middle element here. Compare 3 with target 2. 2 is smaller, then we need to move right pointer to the left of the middle because we need to search the left side. Left is not greater than right. Continue the loop. Recalculate the midpoint 1 and compare middle element 1 with target 2. 2 is on the right side of 1, then we need to move left pointer to the right side of the middle. 3. At this time, left pointer is greater than the right pointer. The loop terminated. The position of target 2, if it would be inserted into the array, is at the left index. 0, 1, return 1, where is number 2 would be inserted in order. Example 3, find target 7 inside the array, or if not there, then find the position where it should be. First thing first, set up the left and right pointer, which point to the first and last elements. As long as left has not surpassed right, find the middle pointer and compare 7 with 3, the middle element. So 7 is on the right of 3. Move the left pointer to the right of 3. Left not surpassed right, find the middle element. Compare 7 with the middle element 5. 7 is on the right of 5. Then advance left pointer to the right of the middle element. Left still has not surpassed right. Continue. Middle pointer also point to 6. Compare 7 with 6. 7 on the right of 6. Move the left pointer to the right of 6. At this time, the left pointer surpassed the right pointer. The loop terminates. Return the left pointer. Position 4. 0, 1, 2, 3. So position 4 is the index or the position where target 7 would be if inserted in the array in order. Alright, let's translate this logic into Python. First of all, set the left and the right pointer point to the first and the last elements. So now we're into the while loop. As long as the left index has not surpassed the right index, do the following. Find the middle position. Integer divide. So in Python, integer division means we divide and we float it down to the nearest integer. For example, 5 integer divide 2 is 2. Instead of regular division, 5 divide 2 is 2.5. 7 integer divide 2 is 3, not 3.5, not a regular division. Alright, keep moving. So we got middle position. Compare if target is the same as the middle elements, then we found the target inside the array, return its position. Else, if the target is smaller than the middle elements, move right pointer to the left of the middle pointer. Else, the last case, do the opposite, move left to the right of the middle element. If the target is not in the array, the loop at some point will terminate. Left will be the position where the target would be if inserted. Return left index or left pointer. Alright, and we're done. Was clean, fast, and to the point. A textbook binary search. Let's hit that submit button. Boom, one shot, accepted. If that helped you cross this problem, drop a like and subscribe for more walkthroughs like this. Catch you in the next one. Thanks for watching. Hello everyone, I'm Alan and this is Leetcode Simplified, where we walk through Leetcode problems the easy way. Today we're tackling Leetcode 58, length of the last word. This problem, short and sweet. The task is simple. Given a string as consider word and space, which may include leading and trailing space, return the length of the last word. For example, the last word in this string is word and this length is 5. The length of moon, last word in this string is 4. The steps are simple. First, remove leading and trailing spaces from the string. Second, break the string into a list of words. Third, get the last word. Finally, get its length. Look at the second example below. Given the string fly me to the moon, step 1, remove trailing space. It becomes fly me to the moon. Next, break this string to a list of words. Fly me to the moon. Third, get the last word in the list, which is moon. Lastly, calculate its length, which is 4. Return 4. Translate these steps to Python. String as, strip all the trailing spaces. Next, split into a list of words. Retrieve the last word in the list. Now get the length of this word using function length. Let's practice writing this one more time. Strip all the trailing spaces, then split it into a list of words. Then retrieve the last word in the list and get its length. That is the result. No need for loops, just a clean one-liner, short and sweet. Done. That was fast, clean, and straight to the point, the Pythonic way. Hit the submit button. Boom, one shot, accepted. If that helped you simplify this problem, drop a like and subscribe. Hello everyone, I'm Alan and this is Leetcode Simplified, where we walk through Leetcode problems the easy way. Today, we're tackling Leetcode 66 plus 1. Given an array of digits represent a positive integer, add 1 to it and modify in place and return the resulting array. Everyone knows how to add 1 to a number on paper. Sounds simple, right? Well, it is, mostly, but we need to handle carryovers correctly, especially when we have trailing lines. Take a look at the below example and let's animate this logic step by step. Just like we do addition by hand, go through the digits from right to left, add 1 to 3, so 4. When we go through digits from right to left, if it's less than or equal to 8, add 1 and return the resulting array. If the digit is 9, change it to 0. Repeat the process. Go to next digit 2, add 1 because it's a carry on. Add 1 to 2 is 3 and return. Done. So the given array is 1, 2, 9. The resulting array will be 1, 3, 0. How about this time it is 1, 9, 9 instead? Again, go through digits from right to left. If it's 9, change it to 0 and go to the next, which is also a 9. Change it to 0 and go to the next, add 1, 2 and immediately return. So after add 1 to the array 1, 9, 9, the resulting array will be 2, 0, 0. Take a look at the last case, which is a special case where all digits are 9. So given the array 9, 9, 9, add 1, go through the digits from right to left. This is a 9, change it to 0 and go on to the next left, which is also a 9, change it to 0. Go to the next left, which is also a 9, change it to 0, and the loop is now ended because no more digit. The for loop exit, add the carryover 1 in front. The initial given array is 9, 9, 9, and after adding 1, we modify it and return the resulting array as 1, 0, 0, 0. Alright, let's code it up. For every position in the reverse orders of the array in full range, if any time the digits is less than or equal to A, you just add 1 to it and return the resulting array. If the digit is 9, set it to 0 and move on to the next left. If we exit the loop, that means all the digits were 9, so we return 1 in front, the resulting digits. Basically, we just return a new array starting with digit 1, followed by all zeros. And we're done. That was clean, logical, and straight to the point. We handled the case where all the digits are 9. Let's mark that submit button. Boom. Accepted. One shot. If that helps simplify the logic for you, drop a like and subscribe for more clear and beginner-friendly walkthroughs.
Hello everyone, I'm Alan and welcome back to Leetcode Simplified, where we solve problems the easy way. Today we're tackling Leetcode 67, add binary. Given two binary strings, return their sum, also as a binary string. First things first, we need to understand how binary addition works by hand. Let's add 1100 and 1110 and observe what happens, column by column. First column, 0 plus 0 equals 0. That's even, so the binary digit here is 0. Next column, 0 plus 1 equals 1. Odd, so we write 1. Next, 1 plus 1 equals 2. Even, we write 0 and carry over 1. Last column, 1 plus 1 plus 1 equals 3. Odd, we write 1 and carry 1 again. Finally, that carry 1 gets written in front, so the result is 1, 1, 0, 1, 0. From this, we can observe two important mental shortcuts. If the total is even, the binary digit is 0. If the total is odd, the binary digit is 1. That's what total modulo 2 tells us. It checks for even or odd. If the total is 2 or 3, we carry over 1 to the next column. That's exactly what total floor divided by 2 does. It gives us the carry. Now let's turn that logic into Python. We start with an empty list to store the result. Set pointers I and j to the end of each binary string. Initialize carry as 0. Then we loop as long as either string still has digits left or there's a carry. At each step, start with the carry as the total. If it has a digit, add it as an integer to the total and move I left. Same for B. Add digit to total and move j left. The current binary digit total modulo 2, convert it to a string, and append it to the result. Update the carry as total floor divided by 2. Finally, reverse the result list and join it into a string. That's your answer. Let's go ahead and hit the submit button. Whoops, there is a typo. Here it is. Let's resubmit. Great, accepted. And that's it. No built-in conversions, no binary headaches, just basic math, a clean loop, and one simple mental trick. Even total, write 0. Odd total, write 1. Carry over if total is 2 or 3. If this helped, drop a like and subscribe for more beginner-friendly LeetCode walkthroughs. I'm Alan, this is LeetCode Simplified. See you in the next one.
Hello everyone, I'm Alan. Welcome to Leetcode Simplified, where we solve problems the easy way. Today, we're tackling Leetcode 69, square root of x. Given a non-negative integer x, find the square root of x. Round it down the integer part only of the square root. Quick example, square root of 8 is about 2.8. But the problem only wants to return the integer part, 2. In mathematical terms, it means given x, find the largest integer m such that m times m less than or equal to x. Here is our approach. Use binary search. Because binary search is optimized for finding breakpoint in monotonic range, exactly fit this problem. Our binary search do not apply to these two special cases, so we handle them here. If x is 0, its square root is 0. If x is 1, its square root is 1. Here is our main focus, binary search. For any x larger than 1, square root of x cannot be larger than half of x. In the range between 1 and half of x, find the middle and compare middle times middle to x. If equals, middle is the square root. If middle times middle less than x, then the square root must be larger than that middle. So move the left boundary to middle plus 1. If middle times middle greater than x, then the square root must be smaller than that middle. So move right boundary to middle minus 1. Repeat the process again and again until left boundary and right boundary cross each other. Then stop and return the right boundary because left boundary had just gone beyond the correct answer, the threshold. And the right boundary is the largest possible number where right times right is still smaller than x. We want only the integer part of the square root. Let's do a walkthrough with the following two examples below to understand this better before we implement it in Python. We're looking for the square root of 4. Now intuitive says the square root of x cannot be larger than half of x. Try half of 4, which is 2. 2 times 2 equals 4. Then 2 is the square root of 4. That's simple enough. Next example. Find square root of 8. The square root of 8 cannot be larger than half of 8, 4. So we will perform a binary search from 1 to 4. Initially, the left boundary is 1, right boundary 4. The middle is 2, and 2 times 2 less than 8, so the square root must be larger than 2. Set left boundary to 3. Middle is now 3. 3 times 3 greater than 8. Square root must be smaller than 3. Set the right boundary to 2. The right boundary is now smaller than the left boundary. A second ago, we already knew that the left was not a good choice, but the right is, because the right times right is still less than 8, so return the right boundary. Let's turn that into Python. First of all, if x smaller than 1, return x, because the square root of 0 is 0 and square root of 1 is 1. Set the boundary for our binary search from 1 up to half of x And as long as the left boundary and the right boundary has not crossed each other, do the following. Find the middle and compare middle times middle to x. If equals to x, that middle is the perfect square root of x. If middle times middle less than x, then that middle is not a good candidate. Must be on the right of the left boundary, and we move the left boundary to the current middle plus 1. Similarly, if greater than x, then that middle is not a good candidate. The correct square root must be on the left of the right boundary. So move the right boundary to middle minus 1. Repeat above operations as long as left boundary and right boundary do not cross each other. If they do, terminate the while loop and return the right boundary, because we just knew that left boundary was not a good choice. Right boundary is still, because rhyme times rhyme is still less than x, so we return the right boundary. Okay, done. That's there all to it. Let's smart that submit button. Boom, accepted. A clean, efficient binary search that gives the integer part of the square root, fast and accurate. No need for guessing, no floating point math, just simple logic the easy way. If this helped, drop a like and subscribe for more beginner-friendly Leetcode walkthroughs. I'm Alan and this is Leetcode Simplified. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're solving Leetcode 367, valid perfect square. Given a positive integer x, return true if x is a perfect square of some integer m. In other words, if you can find an integer m such that m times m equal x, return true. By the way, m is called the perfect square root of x. Here is our approach. We will use a binary search because it is optimized for finding breakpoints in monotonic range. In the case we are searching for breakpoint m, such that m times m equals a given x in a sorted dataset 1, 2, 3, and so on. That's perfect for binary search. But first, let's take care of this special case. 1 is a perfect square because 1 equals 1 times 1. Now, here is our main focus, binary search. For any x larger than 1, perfect square root cannot be larger than half of x. So initially, we search in the range between 2 and half of x. Calculate the middle of that range and compare middle times middle to x. If equals, then middle is m, the perfect square root. Return true. If middle times middle less than x, we want to search the perfect square root on the right side of the middle. How to do that? Move left boundary to middle plus 1. Likewise, if middle times middle is greater than x, search the perfect square root on left side. And how to achieve that? Set right boundary to middle minus 1. Repeat these steps until we find the perfect square root or left boundary and right boundary cross each other. Then stop the process and return false. No perfect square root for that given x. Let's animate below example step by step. We're looking for the perfect square root of 16, if any. Our intuitive says the perfect square root of x cannot be larger than half of x, 16, which is 8. So we start the binary search from 2 to 8. Initially set left boundary at 2 and right boundary at 8. The middle is 5 and 5 times 5, 25 is greater than 16x. So the perfect square root, if any, must be smaller than 5. So we move the right boundary to 4 so that we can search the left side of the middle 5. In the new search range from 2 to 4, the new middle is now 3, and 3 times 3, 9, is less than 16. So the perfect square root, if any, will be larger than 3. To search the right side of 3, we move the left boundary to 4. In the new search range, both left and right point to 4. Then the new middle also point to 4. 4 times 4 equals 16. It means 4 is the perfect square root. 16 is perfect square. Return true. Now that we understand the logic, let's implement it in Python. First, if x equals 1, return true. 1 is a perfect square. Initially, set the search range from 2 to half of x. As long as left boundary not cross right boundary, do the following. Find the middle and compare middle times middle to x. If equal to x, return true. X is a perfect square. If middle times middle is less than x, search right side of middle, so move left boundary to middle plus 1. And finally, if middle times middle greater than x, search left side of middle, set right boundary to middle minus 1. If left and right boundaries cross each other, the while loop will exit return false because there's no perfect square root. And that's how you check if a number is a perfect square, fast and clean. Let's hit the submit button. Boom, accepted. Binary search gives us the answer with no need for square roots or floating point math. Just smart logic and integer precision. If this makes sense, give us a like and subscribe for more simplified Leetcode guys. I'm Alan and this is Leetcode Simplified. Catch you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're solving Leetcode 70 clamping stair. How many distinct ways to reach level N if you take 1 or 2 steps at a time? Let me construct this beautiful staircase and we get down to business. This is the ground, level 1, level 2, level 3, and so on and so forth. Now, let's say you are standing at level 20. How many distinct ways could I possibly taken to get here, you ask? Well, you just climb up from level 19 or 18. Then just add the total number of ways for you to reach level 19 and 18. There are 6,765 ways to reach level 19. 4,181 ways to reach level 18. 10,946 is the number of ways for you to reach level 20. That's it. At any level N, the number of ways to reach there equals the number of ways to reach level N-1 and the number of ways to reach level N-2. Just add the previous two to find the next one. Sound familiar? Yes, this is just the Fibonacci sequence in this guy. How about the number of ways to 17, 16, 15, you may ask? We can find the answer by starting from this. 1 way to reach level 1, 2 ways to reach level 2, 1 step, or single 2 step. Given the 2 base cases, we can find the number of ways to reach any level. 3 ways to reach level 3, 5 ways to reach level 4, 8 ways to reach level 5, and so on. Let's translate this logic into Python. Use interactive approach, no recursion, no memorization, no extra space. Just the best and most optimal solution. We already knew there is 1 way to reach level 1, 2 ways to reach level 2. Set variable A, number of ways to reach level 1. B, number of ways to reach level 2. At each level from level 3 to level N. Set the new A equals to the old B. The new B is the sum of the previous A and B. After the loop, the final B will hold the number of ways to reach level N. Let's hit the submit button. Boom! Accepted. This iterative logic is efficient. Time complexity is O(n), 1 pass. Space complexity is O1. Just two variables, no recursion, no stack overflow, just clean math based on how stairs can be climbed. And that's how you solve climbing stairs. Fast, simple, and clean. Fibonacci in disguise, implemented with a few lines of code. If this helps simplify the problem for you, give it a like and subscribe for more logical Leetcode guides. I'm Alan and this is Leetcode Simplified. Hello everyone and welcome back to Leetcode Simplified. I'm Alan and today we're solving Leetcode 83. Given pointer head to a sorted linked list, remove duplicates in place so that each value appears only once. The modified linked list should remain sorted as well. Because the linked list is sorted, duplicates are next to each other. Just simply reroute the next pointer appropriately. The process will be much simpler than you might thought. Let's walk through two examples below step by step to see how we can manipulate pointer to skip duplicate nodes. First, create pointer curve to point to the same node 1 as pointer head. We use curve to traverse the linked list and manipulate pointers appropriately. Curve points to a node of value 1. Curve next points to a node also of value 1. We want to skip the second one by pointing curve next to curve next. Curve now point to 1 and curve next point to 2. Values are different. Simply advance curve to curve next. Curve is now 2 and curve next is none. That's the end of the linked list. So we return pointer head, which points to the first node of the modified linked list 1 to 2. The next example, given pointer head that points to the first node of the linked list 1 to 1 to 2 to 3 to 3. First, create pointer curve to also point to where the pointer head points to. Compare values of the two nodes that curve and curve next point to. Curve points to the node of value 1. Curve next points to the node also of value 1. We want to skip the second one by pointing the curve next to curve next. Compare again. Curve points to node of value 1 and curve next points to a node of value 2. The values are different. Advance curve to curve next. Repeat the comparison. Curve now point to a node of value 2. Curve next point to a node of value 3. Different. Simply advance curve to curve next. Compare again. Curve now point to a node of value 3. Curve next point to another node also of value 3. Skip the second 3 by pointing curve next to curve next. Now curve next is none. It means the node curve points to is the last node. Return the pointer head, which points to 1 to 2 to 3. If we clear all the steps, it's time to implement them with Python. First thing first, create pointer curve to point to the same node as pointer head. We use curve to walk through the list. As long as curve and curve next are not none, compare their values. If they're equal, point curve next to curve next to skip the duplicate. If different, advance curve to the next node. If curve is none because the linked list is empty, or if curve next is none, no more node, exit the while loop and return pointer head which points to the first node of the modified linked list. Alright, let's mark the submit button. Boom, accepted. Just some clean, simple and efficient pointer manipulation in a linked list. Time complexity linear (ON) because each node is visited only once. Space complexity constant O1 because the process is done entirely in place. If this breakdown makes it clear for you, drop a like and subscribe for more simplified Leetcode tutorials. I'm Alan and this is Leetcode Simplified. Catch you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're tackling Leetcode 88, Merge Sorted Array. We need to fully understand the problem setup first. Given two sorted arrays, nums1 with m is the number of its valid element and nums2 with n is the number of its elements. and the problem automatically adds n zeros to the end of nums1 as placeholders. The total length of nums1 is m plus n. Our task is to merge nums2 into nums1 in place so that the final versions of nums1 is still sorted. Here's how we're going to do it. Since nums1 has a bunch of trailing zeros, we can safely override nums1 from the end with the biggest elements from either array. Let's animate this approach with the 3 examples below. Example 1. Num1 has 3 valid elements. Num2 have 3 valid elements. Therefore, n zeros are added to the end of num1. Given all that, here what we'll do. Set I points to 3, the last valid element in nums1. J points to 6, the last element in nums2. K points to 0, the last element in nums1. Start the iteration process. At K position, place the bigger of 3 and 6 and move J left from 6 to 5. Then move K left. Repeat the process. At the new K position, place the bigger of elements at I and J. 5 is bigger than 3. Move J left from 5 to 2. Then move K left. Repeat the process. At the new K position, place the bigger of elements at I and J. 3 is bigger than 2. Move I left from 3 to 2. Then move K left. Repeat the process at the new K position. Place the bigger of elements at I and J. They are both 2, so place the 2 from J to K and move J left, then move K left. At this time, J points to -1, indicating that nums2 runs out, so we stop the process. That's it. Nums2 has been merged into nums1. Move on to example 2. I point to 1, the last valid element in nums1. J points to -1 because nums2 is empty. K also points to 1, the last element in nums1. The iteration process won't start because nums2 is empty. And voila, that's it. Nums1 is the result of merging itself with another empty array. Finally, example 3. I points to -1 because nums1 has no valid element. J points to 1, the last element in nums2. K points to 0, the last element in nums1. Since nums1 has no valid element, just copy elements from nums2 into the placeholders in nums1. Copy 1 from nums2 to the K position in nums1. Alright, if we're clear on the logic, let's translate that into Python. Start by setting 3 pointers. I points to the end of the valid portion of nums1. J points to the end of nums2. K points to the very end of nums1. This is where we'll place the next biggest element. Now, loop from both position I and J as long as they are greater than 0. If nums2 element is bigger, override nums1k with it and move J left 1 position. Else, if nums1 element is bigger, override nums1k with it and move I leftward 1 position. After nums1k get overwritten, move K left 1 position to get ready for the next largest element. Now, here's the special case. Nums1 runs out of elements, but nums2 still have some left. Just copy them into nums1. Why don't we do the same for nums1? Well, if nums1 has leftovers, they're already in place in sorted order. No need to touch them. It's time to smash the submit button. Boom, accepted. Great. This solution runs in O m plus n time and does everything in place using just constant extra space. Simple, efficient, and easy to understand once you visualize the pointers working from the end. And that's how you merge two sorted arrays in place. If the explanation helped you, give it a like and don't forget to subscribe for more simplified Leetcode tutorials like this. I'm Alan and this is Leetcode Simplified. Thanks for watching. I'll see you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're going to walk through Leetcode 94 binary tree in order traversal. Given the root of a binary tree, return an array of all nodes value in order sequence. We will use an iterative approach to learn the logic step by step, simulate a system called stack that recursion would normally use. Let's first quickly revisit what in-order traversal means. In binary trees, in-order means we visit nodes in left, root, right order. Here's my two-phase process. Phase 1. Use pointer curve to go left as far as possible and append nodes along the way onto the stack. Phase 2. When you add a node with no left child, pop the stack and go to the pop node. Add its value to the result array, then go right. Repeat the two-phase process until no more nodes or stack is empty. Let's walk through example 1 step by step. Given pointer root that points to node value 1 of binary tree 1, node 2, 3. First of all, create pointer curve to point to the same node as root. Curve will be used to traverse the whole tree in order. Let's begin the two-phase process. Phase 1. Curve goes left as far as possible while appending nodes along the way to a stack. Append to the stack node value 1 before move curve left. Curve now points to none, means no more node. Then phase 2. Pop the stack and points curve to the pop node value 1. Write its value 1 to the result array and move curve right. Repeat the two-phase process. Phase 1. Append to the stack node value 2 before move curve left. Append node value 3 to the stack before move curve left again. Curve now points to none, so begin phase 2. Pop the stack and points curve to the pop node 3. Write value 3 to the result and move curve right. Repeat the process. Curve is none. There is no left sub 3 to go, so skip phase 1. Phase 2. Pop the stack and points curve to the pop node 2. Write value 2 to the result and move curve right. Now curve is none and the stack is empty. We end the entire process. Return the result array which contains all the nodes value in order traversal. Let's move on to the second example. Given pointer root that points to the node value 1 of binary tree 1, 2, 3, 4, 5, node 8, node 6, 7, 9. First of all, create pointer curve to point to the same node as root. Curve is used to traverse the whole tree in order. Begin the two-phase process. Phase 1. Curve goes left as far as possible while appending nodes along the way to the stack. Append to the stack node value 1 before curve goes left. Append node value 2 to the stack before curve goes left. Append node value 4 to the stack before curve goes left again. Curve is none, no more left to go. Begin phase 2. Pop the stack and points curve to the pop node 4. Write value 4 to the result and move curve right. Repeat the process. Curve is none, no left. Skip phase 1. Phase 2. Pop the stack and points curve to the pop node 2. Write value 2 to the result and move curve right. Repeat the two-phase process. Phase 1. Append node value 5 to the stack before curve goes left. Append node value 6 to the stack before curve goes left. Curve is none now. No more left. Phase 2. Pop the stack and points curve to the pub node 6. Write value 6 to the result and move curve right. Curve is none. No left, so skip phase 1. Phase 2. Pop the stack and points curve to the pub node 5. Write value 5 to the result and move curve right. Repeat the two-phase process. Phase 1. Append node value 7 to the stack before move curve left. Curve is none, no more left. Phase 2. Pop the stack. Points curve to node 7. Write value 7 to the result and move curve right. Curve is none, no left, so skip phase 1. Phase 2. Pop the stack and points curve to the pub node 1. Write value 1 to the result and move curve right. Repeat the two-phase process. Phase 1. Append node value 3 to the stack before move curve left. Curve is none, no left, so skip phase 1. Phase 2. Pop the stack and points curve to the pub node 3. Write value 3 to the result and move curve right. Repeat the two-phase process. Phase 1. Append node value 8 to the stack before move curve left. Append node value 9 to the stack before move curve left. Curve is none, no more left. Phase 2. Pop the stack and points curve to the pub node 9. Write value 9 to the result and move curve right. Curve is none, no left, so skip phase 1. Phase 2. Pop the stack, point curve to the pub node 8. Write value 8 to the result and move curve right. Finally, curve points to none and the stack is empty. We end the two-phase process. Return the result array, which contains all the nodes value in Inorder Traversal. Alright, are you still with me? Let's jump right into Python. First of all, create an empty stack and an empty result array. Next, create pointer curve to point to the same node as root. Now, begin the two-phase process that will run as long as curve is not none or the stack is not empty. In phase 1, keep moving curve left as far as possible. Append the node to the stack along the way. Phase 2 begins when we add a node with no left subtree. Then pop the stack and point curve to that pub node. Append the pub node value to the result array and move curve right. Finally, when curve is none and the stack is empty, end the two-phase process. Return the result array, which contains all the nodes values in Inorder Traversal. That's it. It's time. Let's mark the submit button. Boom, accepted. This solution runs in O(n) time, where n is the number of nodes, and use O(h) space, where h is the height of the tree due to the stack. It's a clean, reliable method and avoids the recursion limit for large trees. Understanding how to simulate recursion with a stack is a powerful skill in tree problems. If you can walk the control flow like we just did, you'll be in great shape for many more tree questions. Hope this makes sense and help clarify how interactive Inorder Traversal works. If it did, give it a like, drop a comment with questions, and don't forget to subscribe for more step-by-step Leetcode walkthroughs. I'm Alan and this is Leetcode Simplified. Thanks for watching, and I'll see you